So today we're discussing designing springs, and this is one of the important components we will need to discuss because we need them for various purposes on our engineering components and mechanisms and name it. So springs are very important. And as usual, so here there's a definition where we try to say that a spring, this is supposed to be an elastic body, and why it's there is to deform under load and retain its original shape after the load has been removed. So here you will notice that in engineering applications, we use them in a variety of ways for shock absorbers in aircraft, motor vehicles, plant machinery, vibrations and dampers, and name it. Also, you have mechanisms like brakes, clutches, levers, and spring-loaded valves that make use of the same springs. So when you apply brakes, a part behind there's a cylinder, and then there's a spring which is already sitting there, such that when the fluid pressure goes away, the spring return pushes the piston in its place. Different mechanisms, different arrangements, but all that making use of the springs. In some other cases, we use the same springs for controlling motion, keeping members constantly engaged, like in cams and follower mechanisms, and many other. And if you talk about spring balances and engine indicators, these are there to measure forces. They also utilize a spring. If you've also heard about a strain gauge, which we use for the same purpose, where we could be trying to look at how much force is here, where we are applying Hooke's law, it also uses a spring. So all those are just used for that. Storing energy in watches. Interestingly, these watches may no longer be on the market, but the principle of operation still remains. We have those watches that were designed. They used to have a spiral spring. So all you do is wind that spring, and when it has been wound to the right degree, the watch will run, sometimes for a full day or more. Then after that, you do the same. Meaning those watches never used to have batteries, but they were utilizing the same spring. So that spring will be releasing that energy slowly, but in a very timed way. And in the end, you have some second hand, some minute hand, and all that. They were there to now help in quantifying what time it is and so forth. In governors, we use the same for regulating the performance of an engine. So all that utilizes the same springs. When we talk about types of springs, we normally have two broad versions. We have those springs that are good in tension, the ones that deal with compressive force, others tensile. I mean, compressive and tensile. So here what you see is we have the ones that are called helical springs. Following the shape of an helix is how they are designed. And like this, the same shape of a helix can handle the two versions we've talked about. So you can have a compressive helical spring. You can also have a tensile helical spring. So depending on whether it's handling a tensile load or a compressive load, that's how you categorize them. Then we also have conical and volute springs. As the name suggests, a conical spring forms the shape of a cone. And of course, it will be wound following a normal shape around a particular center. And with different applications, you see it also coming up. Then we also have what are known as torsion springs. We have leaf springs. For motor vehicle applications, these leaf springs are quite critical because they are there to help us dump those loads around mostly for heavy machinery. Then we also have disc springs. talk about the springs that, in fact, similar to the ones that may also look like diaphragms. Yeah, so here we have those that could be used for holding together a central bolt or tube. All those are the uses. Now, you see, when we talk about machine design, this part, usually most of you think, these are just explanations. Why can't we jump to calculations? Deliberately, you see that some questions start with these explanations. Because when you're doing machine design, you need to understand what it is that you're working on. Before you can even go into the deep analysis, you should have the basics of what you want to achieve. Why do I need a spring? What types of springs do I have? Do I really need to use a spring? Can't I use other mechanisms? So that's why this information is critical. You can take your time to look at that and add even more. Now, there are also some terminology. There are also some terminology that is critical when it comes to the same springs. So here we're talking about, if you look at this spring diagram we have here, the wire of your spring, the material of your spring is made of this wire, whose diameter is coming with small letter d. Then the distance from one spring coil to the next, a point on one spring coil to the point on the next spring coil, this gives us the pitch. Then we also have the coil diameter, d, it's just d. This is like the mean diameter of your spring from the center to the center. We're not talking about the outer diameter or the inner diameter. It's just the mean diameter of the whole spring when it has been coiled. And added to that, you realize you may have a load that is acting on your spring and the torsion T, which tends to twist your spring when it is on operation. So these are the factors that we could be looking at. And here, what you see here now is ourselves trying to talk about the specs that we consider to be important when we are talking about sizing a spring or specifying the parameters of a spring. D, this one we've already talked about. T, the twisting moment or the torsion. G, that's the modulus of rigidity. Then we also have W, the actual load acting on the spring. Then we have N, number of active coils, and C, this is the spring index. Now, in the spring index, we're talking about the ratio between this D for the coil that has been made by your spring and the diameter of the wire of the spring. So D divided by D, you have that spring index. Small letter n talks about the number of active turns of the coil. So how many active coil turns do you have for this spring? Is it 10? Is it 15? That is the small letter n you see there. And of course, P, like we said, P is the pitch of the coils, and small d, that's the diameter of your spring wire. Then when we come to the deflection that your spring is going to go through, that deflection can be denoted by X or sigma. That is a spring deflection under load. So when this load is applied, you notice that this spring is going to compress by how much? By that. So we'll come up with expressions to tell us how you can arrive at that. Now here, we go to the twisting moment of a spring. It's just force times radius. So T is W times R. R, this is the distance from the center of a spring to where we called the mean diameter, where we labeled it. So, or to the center of your wire material. So meaning R is D over 2. And D is the mean diameter of your spring. So when you do that, it becomes your torque, therefore, or your twisting moment is this load times D over 2. So when you proceed now to compare this now with stress, because we know that stress is force over area. Stress is the load over area. And we also know that area is pi d squared over 4. So what do we do then? We can make this W the subject of the formula. But before we even do that, where there is area here, we can expand with this formula. We put pi d squared over 4 in place of the A. So there you have your stress, your shear stress being equal to 4W over this pi d squared. Then therefore, your W, if you make W this time around, it will be shear stress times pi d squared over 4. In other words, we've always said that whenever you want to get your force, it's supposed to be load is equal to stress, supposed to be equal to force times the area. So in this case, our force, we're using W. W times the area. And noticing very well that the area is pi d squared over 4. That's why you have this shear stress times all that. Oh, sorry, not force. This is supposed to be stress. And we're using shear stress here, the shear stress. So shear stress times the area. Let me just make a quick correction there. We erase. So we're saying that load, the W, is the stress times the area. And since we know that this area is pi d squared over 4, we plant it back in the expression and we have that number. Let's combine the second equation and the first equation. Where we came from, we said that equation number 1, we said T, the torque, is that times d over 2, and we left it like that. That was our equation 1. And then if we now bring out equation 1.2, which is this one, you notice when we decide to combine them, we end up with the formula for shear stress as being equal to 8WD over pi d cubed. How? You can notice that in the second equation, the one we called, the first one, the first equation, it had d over 2. So all we are doing now is do a quick substitution to make sure that we take care of the torsion, because that's how it becomes easier for us. So from there, you can notice our expression for shear stress is that AWD over pi d cubed. Then here, when you bring out direct stress, it becomes 4W pi d squared. Now here, remember, the parameters provided, the D on top and the D below, they're different. These are two different parameters, and of course, they have to be differentiated. So the maximum shear stress, when you compare the shear and the direct stress, put them together, it means you have to add this expression and the other expression, so you get your maximum shear stress for this material. So AWD over pi d cubed plus 4W over pi d squared. So if you go ahead and factorize AWD over pi d cubed, you have 1 plus d over 2d. Now, to make our life easier, you don't even need to stress here. This d over d, the spring index, can be represented by letter C because it's a constant. So that being the case, you will notice we'll have AWD over pi d cubed, then 1 plus 1 over 2c. So it means these two are already taken care of by letter C, and we are good to go. Then to make it even much smarter, there is what we are going to call the shear stress factor. The shear stress factor is represented by Ks, and it takes care of all this. And I have to bring out here that apart from this one, there are also other constants that we bring in. But for the sake of making this smooth and smart for us as we introduce this topic, we'll first of all ensure that you understand this factor before we bring in others when we are solving questions. So meaning this was expression where we had all this, we end up with Ks and then AWT over pi d cubed. That's the maximum shear stress. All right, now what about if we're looking for the deflection of a spring? The deflection of a spring, it goes back to the torsion equation. And when we put them together, remembering R is D over 2, we have also sigma is D theta over 2. Bring all of them together. Our sigma, our deflection, our deflection is AWC cubed N over GD. And therefore, this is the expression that we're supposed to use whenever we're discussing the deflection. So if we say we're looking for the spring constant is given by load over W over the sigma. So if that is what you're looking for, then K is W over that, and it becomes just this. Unless other factors have been provided, but it's going to be as simple as that. Great. So like we keep saying, you don't need to worry about the fanciful formulas we've talked about. Here, our mainstay is to apply. Just like a footballer who is very good at dribbling, if they don't score, it's a sheer waste of time. They need to score goals. So let's get to the examples and apply the principles we've just discussed. So here's our example. Example 1, it says, we have a compression helical spring of external diameter 80 millimeters. It is to be made from a wire of diameter 5 millimeters. The maximum permissible shear stress in the material of the wire to be maintained at 400 megapascals. Modulus of rigidity, 90,000 newtons per square millimeter. Determine the number A, suitable actual load for the spring, maximum deflection for the spring pattern, stiffness of the spring, number of active turns of the spring. Okay, just like that. So those are the 4 items we need to find. Now, if you look at this question, the first question you need to look at is that you have not been provided with the mean diameter. No. What you can see here is actually the outer diameter, D, O, outer diameter. That's what they have given us here. And if I take you back to the expression, to the formula that the diagram that we had here, this is our D. It talks about the mean diameter, and this is the one we're talking about here. Even the formula we have is actually capturing this one. So in the case of the example we have, this is not what we've been given. What they have given us is the outer diameter, meaning we have to take care of the process of now finding the mean diameter. So let's see, how do we do that then? Well, the process is quite simple. So what are we going to do? To find the outer, first of all, the outer diameter is there, it's 80 millimeter. So all we have done is to not just leave it in millimeters, though we know it will be useful like that at some point. 80 millimeter, we convert it to meters. So 80 millimeters divided by 1000, you have 0.08. Then I also have the wire diameter. The wire diameter is actually 5 millimeters. Now we convert also to meters, we divide by 1000, then we get this 0.005. Then proceeding from there, we also have the maximum shear stress, which we've been provided here. The maximum permissible shear stress there is 400 megapascals. And per tradition, we say that mega represents a million or 10 power 6. So we have 400 times 10 power 6, which gives us 4 times 10 power 8. Where does the 8 come from? Because of these other 2 zeros added to that. So you have 10 power 8 instead of 6. Next, this is the G, modulus of rigidity. It's 90,000 Newton per square millimeter. So here we are done with the information that we were given. Suitable axial load for this spring. How do we find it? First of all, our first stopover is to get this D. To get this D, since we've been given the outer diameter, you just subtract the wire diameter and you're good to go. So outer diameter minus wire diameter. So the D, outer diameter, is 0.08 minus the wire diameter, which is 0.005. Our answer is 0.075. Then, what about the spring index? The spring index is C, which is capital D over small d, and we have 0.075 meter divided by 0.0075. So 0.075 divided by that. And what you get is that as our number. Now, we'll continue. What about the next? We also have the case. We are talking about shear correction factor. This is the one we said is supposed to be 1 plus 1 over 2c. 1 plus 1 over 2c. Now, let's get something straight here. 5 into, here we're saying our C is actually 15. But then, there's something that I want you to observe clearly. This 5, it's like we're saying it's 50 millimeters, which is not correct. I think we can make that quick correction. The number here is supposed to be 0.005. And I think it will affect this one as well. So 0, in other words, what we have is 0, just a minute, 0.075 divided by 0.005. 0.005. So 0.075 divided by 0.005. That is how we arrive at the 15. You can, of course, when you enter it in your calculator, to give you that. So here, it was just a typo error that we wrote 0.05, but it's supposed to be 0.007005. Yeah, so that's that one there. But otherwise, this doesn't change the answer we have here. The answer we have here is still okay. Then the shear stress factor continues from there. 1 plus 1 over 2c, meaning 1 plus 1 over 2 times 15. And we end up with that. 1.033333, just like that. Next, maximum shear stress, we know, is supposed to be this. Ks AWD over pi d cubed. So we can do the substitution. W, we make our W the subject. It will be pi d cubed times maximum shear stress over 8 Ks and the D. That's how you get that. Of course, not forgetting our shear stress, which is already on top. Now, here we do the substitution, but if you want here, you can go ahead and substitute. After you substitute, then you just allow this to stand out. But here we made W the subject, so maximum shear stress times by d cubed over 8 dks. So the maximum shear stress is 4 times 10 power 8. Then we have the pi. D is 0.005. We raise it to power 3. Divide by, here you open the brackets, 8 times D. The mean diameter is 0.075. Then KS, this is 1.0333. This is our shear correction factor. So from all that, the force on the spring is this, 253.362 newtons. 253.362 newtons. That's the force you get from there. Next, let's go to the maximum deflection per turn. The maximum deflection per turn, as you may remember, we said it can be represented by this, or you may decide to use letter X to represent that deflection. So it's 8WC cubed NGD. Now it's per 10, meaning this 10 is 1, or we can rearrange it. Deflection per 10. So deflection over N, which is 8WC cubed over GD. So 8 times W, the one we found is 253.362, times our C is 15, so times 15 cubed, over G is 9 by 10 power 10, times D, the wire diameter, 0.005. And with all that, we end up with the maximum deflection per turn, that, or is it X, coming out as 0.0152. 0.0152. If you convert this to millimeters, it's 15.2 millimeters because you just multiply it by 1,000. What about the stiffness of the spring? The stiffness of the spring is normally how much force do you need per unit deflection. So it's like we're saying, what is W over sigma? That's the arrangement. What is W over sigma? Extracted from the expression. So in that case, you have GD over 8C cubed N, and that's our K. So we can just substitute. Now here is one thing we can do. If you want, you can use G, the D, 8C cubed N, but if you look at this expression, it means you can either use this pair or you can use this other expression here to get to your K. But to make things faster here, we decided to pick this part. W over sigma. Our W is 253.362 divided by sigma, which is 0.0152. And of course, from there, we have 16,668.553 Newton per meter. That is our K. Spring constant, spring stiffness. Let's go to the number of active turns of the core. Now that we found the stiffness of the spring, we can make use of it, now making use of the other formula which we didn't touch. So GD over 8C cubed. So we have GD, C is our constant, and the number of turns. So we can rearrange our formula to make N the subject, such that in that case, our N will be equal to GD over 8. It's just a K. It's like these two. They will just switch positions, you and this one. So we'll have 8K, then C cubed. Our G is 9 times 10 power 10, D 0.075, and then 8 times K is the one we're from finding, then times C cubed. Our C is 15, so 15 cubed. So once you do that, you get our value as 14.9999 something, meaning the active number of turns, the number of active turns is actually 15 for this coil. And when you talk active turns, we're saying that it's possible that you may have maybe some little turn, some inactive turn, a very small one. The way the top of a spring is done, it's almost flat. So see that when you are counting, you practically may not count that. That's why it's quoted here by this word active. so that we stick to the turns that are going to participate in the damping of a force or in transmitting the force that we're dealing with when this spring is in operation. So this is about how we handle springs. This is how we handle springs. And this is our exercise. Of course, you can see we have answers there. You can give it a try, and then where there's need for clarity, you let me know.